years ago, 65 years ago. And in 1999, it looks like that. Sorry, how do I click next? Ah, yes. So in 1999, it looks like what your man has in his hand. Can you see my green arrow?
Yes.
Okay, good. And so if you zoom on that, that's a little mouse, and it's a 1 gigabyte, but that's 20 years ago. The interesting part of that photo is that you have a disk full of ones and zeros. They're magnetic with nano layers, etc. You have a motor to get it to spin, and it's magnetic. Then you have the head here at the end of that arm, and that head is magnetic when you want to write. It just happens to also be another head that's magnetic when you want to read. And here there is a voice coil which happens to say go and read, and it's magnetic. And hiding in that corner, I don't know how to get rid of the videos of everybody else, but yes. And good. And behind here you have another magnet that says, wow, I am falling. My gravitometer accelerometer has noticed that I'm falling from the hands of the user, so I will hide the head away so it doesn't scratch the disk. And at the end of here, there's another magnet. So they're all real magnets, built very small, apart from the ones and zeros on the disk, but it's full of magnetism. And now they don't exist anymore in that size because you've got SDDs and all that, SSDs. So back to my normal talk, but that to give you an idea of how small things get. And I also did some miniaturization from 12-hour class, so it's stuff, to a 45-minute class, which is micro stuff. And this is the plan of my talk. Blah, 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 images, blah, 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 more images, blah, 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 images, and then the time cuts and I stop showing you images. So you won't have to remember any equation. So micro stuff, MEMS have always been shown as little ants because they're very small and they're very strong. They can be minute, and MEMS were originally electrostatic most of the time for force. It just so happens that when ants become magnetic, they become mighty, and that's when things get funny. So micro stuff, but mighty. So here I'll be showing you plenty of things either stolen from the internet or from our own archive of toys and playing with all my colleagues in Grenoble and other places. And at the bottom we've got all the logos of all the people who give us money to survive. So here you've got on the left, you've got turbo generator, planar. I'll show that later. The diameter is 8 mils in here, millimeters. In the middle, you've got a cube, well, several cubes, but each cube here is 1 millimeter square cube. And you've got in the middle a flying magnet, on the side 2 embedded magnets, and then coils, and then things starts moving around. I'll show you that a little bit. Here you've got something like 0.5 millimeter in diameter, and it's a bi-layer, not morph here, but a layer of piezoelectric and a layer of magnetostrictive. And when you energize the piezo, it stresses the magneto, and then things funny happen. And if you stress the magnetostrictive with magnetic fields, then it stresses the electrics, piezoelectrics, and then you also get interesting stuff at the end of the electrodes. And you can also go further, and Nora will talk more about that. And here you've got little squares of magnets on which are trapped magnetic bacteria. It's a very short summary of the reality. And here on the right, you've got bubbles, not bubbles, but micro droplets of water flying in a magnetic field, and that's diamagnetism. And all those are possible either because they're magnetic or because they're small, or both. So MEMS are microelectron mechanical systems. So basically, you start from microelectronics with electrons. Oh, is everybody hearing properly, or am I speaking too loud, or too slow, or too fast?
Oh, no, it's okay.
That's fine. Okay. So MEMS, you start from microelectronics. So you have, well, that's a rough image on the left here of little electrodes saying, yeah, you shall pass or you shall not pass the information with one electron from the left to the right because I put a field in my semiconductor, blah, blah, blah. Nothing moves, electrons move. And then some guy says, hey, if we take away that layer of insulator or something and the aluminum electrode is free to move, maybe we'll have electrostatic forces and we'll get things to move. And those are the first MEMS. And you can either shake the stuff and they move relative to each other and you start measuring a movement by change of capacity, or you put a voltage and they attract and they start moving. And then someone puts too much electricity in those wires, they heat up, they dilate, they go a bit too long or too short, and because you have a bimorph here between silicon oxide and aluminum, then you can bend it or unbend it. That's less than a millimeter long. And here is a little screen that will stop or not stop the flux of a photon beam from a fiber optic or something like that. And then much later started coming other stuff which needs, so other stuff meaning magnetic stuff, but also piezoelectric, fluidics, shape memory, you name it. But for that you need new materials that are not accepted into the micro technological tools, clean rooms and all that. You need high currents. You need thick films because otherwise high currents burn the conductors. You need plenty of stuff. So it takes time from MEMS to non-electrostatic MEMS, magnetic, piezo, shape memory. And that's where we are today. I go fast because I'm trying to give you 12 hours in 45 minutes. But every time I show you a photo, you can go online and say, wow, that was fun. You put the name of or whatever keyword goes through your brain, and you'll find hundreds of images of research papers, of labs, of YouTube tutorials. So my speech today is just a door. You knock on the door and you go in the room and you try and find whatever. And then why am I here today? It's because MEMS are fun, magnetism is fun, but together it's even more fun. And by doing both together, you open doors that neither can open alone. And my mouse can't open. Okay, so first thing, magnetic interactions, they're remarkable. First is because you can have large forces. In the gap between two iron poles with an electromagnet or you name it, you have 4 bar, 4 atmosphere of pressure every time you have a Tesla. If you have 2 Tesla, you square that, so it's not 4, it's 16, it's not 8, but 16, etc. To give you that in square millimeters, that's a half a kilo, 40 grams. That's a hard-boiled egg on the top of a 1 millimeter square needle. If you have 1 Tesla, but 1 Tesla, you can do it not easily, but you can. And that's because that pressure, that energy is half of B squared by mu 0, whereas in electrostatics, it's half of E squared by epsilon 0. And if you put the numbers with a conservative value of 1 Tesla in a gap, you can store 500,000 joule per cubic meter. Whereas with electrostatic energy, at breakdown voltage of 3 megavolt per meter, you cannot go higher unless you start using, funny gases, or you're stuck at 40 joules instead of 400,000. So that's why you have no electrostatic actuator in real life. You have them in microsystems, but not in macroscopic systems. Now, you can go a bit further with electrostatics, but that's the rough rule. Second reason why magnetism is great is because you can go far. 2 magnets, well, micromagnets, they still see each other at 10, 100 micrometers. And therefore, you can start playing on bigger distances in microsystems. And you do that without contact. You don't need to put the wires there. You can even play through skin, through a seal membrane of a vacuum-packed device, etc. And you can do that without contact. So you can also do suspension and levitation. So you can get rid of friction. You can get rid of touching the edges and therefore contaminating, and etc. You're stable, or you're bistable if you wish. 2 magnets stuck to each other, if you switch off the General Electric switch of the house, the 2 magnets don't fall apart. They're there forever. So you can use that as stability or bistability, left and right, if you want. So it brings interesting assets to actuators. And also you can be bidirectional. If you reverse the currents, then you can repulse, attract, go left, go right, etc. Now, if you start from actual actuators and generators of our size, millimeters and meters, and then you say, well, what happens if I make everything smaller? And if you do a homotetical reduction, scale reduction of all that, most of the time, not always, but most of the time, the volumic forces, the forces per unit volume of device, either they're as good as before or they get better. So 3 examples. On the left, the interactions between a magnet and a magnet, 2 magnets stuck to each other, that gets better by a factor k. If you divide everything by 10, the volumic force is multiplied by 10, which means that here we have a micro switch here that's a quarter of a millimeter long by 5 or 10 microns thick. He has the right to move from right to left in that little square cup at the bottom, and on the right he touches 2 magnets that are embedded, and those are bad iron nickel magnets. They're not really very good in resonance. You've got 0.3, 0.4 Tesla resonance. However, they're so small and the gradient so strong that you need 1000 G of shock if you want to unglue them from each other. Here in the middle, the forces between a magnet and a conductor, what you have in most motors and drives and actuators, is conserved. I will show that with a few formulae later on. Is as good as big as small. So if you have a good motor big, you make it small and it's still the same power to volume ratio. Now, it so happens that the little wires here, they can accept much more current density, the number of amps per square millimeter of section of conductor. That gets higher and higher, I'll explain. And so not only it's as good as before, but you can actually pump turbocharge with more current per square millimeter and have even more power, volumic power. And on the right, it's something quite funny. It's diamagnetic forces. And those, you don't see them in daily life. Nobody sees that. And then if you start going smaller and smaller, then here on the right, you see a gradient dB by dz. And as you get smaller and smaller, the gradient gets higher and higher. And then you start having force that you can actually see and measure. And then you can do funny things with that. So let's start with the simple. First, the magnets, permanent magnets. If you take a neodymium or samarium, you name it, a 1 cubic centimeter, roughly, magnet on the left, magnetized with the quality of magnet that's, let's say, a good samarium or a bad neodymium iron boron of 1 Tesla magnetization. And you have another magnet that's 1 cubic millimeter instead of cubic centimeter. The numbers are not exactly right, but let's assume it is. And it's also made from the same material, magnetization 1 Tesla. So what happens here in point P, you have a field H in air, or then multiplied by mu0, and you have the induction in air. And that field H, as Mike showed earlier. So what I've done here on this image is separate the magnetization value, the amplitude of 1 Tesla without an arrow on it, from its direction, little j, which is a vector, this one. The same with the distance is r, big R multiplied by the unit vector r, etc. So the field H in that point P is j over 4 pi mu 0, a volume of magnet divided by distance cube at which I am measuring. And here, a bracket showing you that if you go left, you've got sines and cosines playing around. And if you're further or nearer, it falls in such and such a way. But it's only unit vectors in that thing. So then you put that all in the computer, and the computer happily computes the field and field lines around your magnet. So left and right. So right, it's too small, so I'll zoom it now. And what we can see is that the field lines that go around and around the magnet, they have the same shape from left to right. And so that topology of the field is preserved. You know why? Because it's only here in those parentheses with J and R, but they're all unit vectors. Nowhere can you see the dimension of it. Big or small, you don't care. It's just directions and proportional distances. And it also shows that if you're in front here, it's a big arrow. And if you're on the side, at same distance, it's half a size arrow, so your field is half the value here than here because of sines and cosines. Now, if I want to see what's red or blue or orange or pale blue, I have to measure, and that part is measured here. And what I see is that here my very angle here is orange, so let's say 0.6. Here orange, 0.6 Tesla as well. But that's a smaller magnet. Yep, but it still has 0.6 Tesla on its edge. And if you go one magnet length ahead, you're in the blue here and you're at 0.2, for example. And here, one magnet length here, blue, 0.2 as well. So my magnet, wait a second, it's 1,000 times smaller in volume, 10 by 10 by 10, and yet it still gives 0.2 Tesla. Yes, but at a smaller distance, but it still gives those Tesla. Now, the fields are preserved, and that's because you've got V, which is a volume, so it's a distance cubed, a size cubed, and at the distance R, but that's proportionally measured, which is also cubed, so all that goes away. Here, that's the same value from magnet to magnet, and that doesn't move. So non-intuitively, if you have a very tiny magnet, on its surface, you will still have the same strong magnetic field as on a huge magnet. But the distances, the field falls quickly. Now, here I have 0.3 and 0.1 Tesla, so I'm losing 0.3 Tesla from there to there. Here as well, but I'm losing them on a distance of 10 millimeters, whereas here I'm losing 0.3 Tesla out of 1 millimeter. So my gradient, my magnetic gradient, is 10 times stronger. And in fact, the gradient is what often makes a force on a magnetic moment. If I bring near that magnet, if I bring a little magnet, it will see a much stronger gradient, and therefore the volume force, the force per unit volume that it will be subject to, will be 10 times stronger. Of course, if I approach 1 centimeter away, I won't see much. So I'm as strong or stronger, but only within a shorter distance. But that's great in microsystems because we work at small distances. I will skip that one because it just shows you what happens if you bring a little moment on the big or on the one, but the force is basically the torque making him rotate is as good here as here per unit volume, but the force is way stronger on him than on him. Now, what can I do with that? If I have a magnet, that magnet here, I don't even care what his size is. Is it 1 centimeter, 1 inch, 1 foot, 1 micron? I don't care. At such a distance, the field is 0.3 Tesla, and here 0.6 Tesla. Now, if I put a conductor in front of it, the current in the conductor sees a magnetic field in blue, and that gives us a force in green, and you have the usual formula that we all know. And if I cut down my current I into a current density J multiplied by a section, an area of conductor S, it's still valid. But then that S, if I multiply it by the length of the conductor, that SL becomes the volume of the copper. So the volumic force, if I divide all this by volume, F divided by the volume, the force per unit volume of conductor, in this case, is proportional to the current density that copper accepts, multiplied by the magnetic field into which it is bathed. Which means that whatever the dimension of my thing, if I have a coil or a conductor in front of a magnet, if I use copper that does not accept more than that much amps per square millimeter, and if I have a permanent magnet that still is neodymium, I will always have, let's say, 1 Newton per cubic centimeter of actuator. If I make it smaller, it will be smaller, but the force will be smaller, but I will still have the same power or force per unit volume of actuator. So that's great. It means that you can make several small actuators instead of one big one, and then they will be as good. Now, if I only take a current conductor, the red one is a conductor. Here it has a current, so the field around it, H, is I divided by the distance that it's going around. So it's I by 2 pi R. which is proportional to the current density in the section divided by distance. So which is proportional to square distance to distance, proportional to distance or dimension. And therefore, if I make everything smaller, I will have smaller by 10, for example, the section is 10 times narrower and 10 times lower, and I measure 10 times nearer, I'll have 10 times less magnetic field around the wire. So it's not as good as a magnet. I am losing. Now, if I wind that wire into a round solenoid, it's exactly like if I had several non-infinite wires, so the same rule applies. So the field in a coil, if you reduce all dimensions by a factor 10, 100, at the same density of current, your magnetic field will fall off. Now, if I put besides that wire a second wire, that wire, the second wire will see a magnetic field 10 times smaller if everything is 10 times smaller, and therefore the efficiency of volume force between two wires talking to each other is falling off. You don't want that. That's with a constant current density. Let's assume that copper burns at 5. Now, okay, that's just to say the same thing, sorry. So if I summarize that quickly, if I have a magnet or a current, they create, when I divide everything by 10, you know, all sizes by 10 and distances by 10, magnets create fields that are as good as before and gradients that are better. Currents are worse on field, but because distances are smaller, they give gradients that are not as bad. They're the same gradients, big or small. So this is what we will keep in mind when we want to use magnetic actions. If we can, we use magnets. If we cannot, we use conductors and coils. Now, a coil, let's assume that I want my coil that's 10 by 10 by 10 millimeters to behave magnetically, to send and emit the same magnetic field around it as a magnet of, say, 1 Tesla of same size. Basically, I want the same magnetic moment. I will need to increase the current density logarithmically every time I divide the size. So a coil the size of my fist or the size of my finger, no problem, because it's 5, 10, 50 amps per square millimeters needed. That's everyday life. And as you go smaller, it's hundreds of amps per square millimeters, thousands, hundreds of thousands. How do you do that? You need to cool your coil. Basically, if you want your coil to be as good as a magnet, as it gets smaller, you need more to pump more current into it, current density. Now, if you add a magnetic core, ferromagnetic core to your coil, then that helps an awful lot. But after a while, you're still stuck, but that's better. If you go towards big machines here to the right, you're happier. Well, you used to be happier before neodymiums became cheap, and now they're not cheap at all. So that's another story. So it so happens that coils do not like to be miniaturized. We've seen that. However, we can play on J here. We can play on the current density because they're small, we can cool them. So maybe we'll gain a bit of the loss. Why can we give more current densities? Because you heat by the volume, but you cool by the surface. So the ratio of cooling surface d squared divided by the volume that heats, d cube, is 1/d. So it improves as you go smaller. B, the distance between the hot source inside and the cold source outside is shorter. So the thermal flow is dependent on that gradient. So it's stronger. So it heats quicker. Also, normal wires in daily life, they're cylindrical. They're like a full toothpaste tube. But planar conductors in micro technology, they're planar. So they have much less volume heating for the same amount of surface cooling. And moreover, you actually make them onto a big piece of silicon, and silicon loves to suck heat and transfer it somewhere else. So all those reasons mean that instead of 5 amps per square millimeter, you can go to 1,000, 10,000, a million if you want. If you pay the price is, okay, I can actually put all those amps in there, but they will heat like hell and I have to get rid of that heat somewhere. And also they will empty my battery. But if I accept that cost, well, then why not? So what can you do with that? A few examples in daily life. Every time you have a MOSFET, every time you have a power transistor, inside those tiny wires, you've got 1, 2, 5, 20 amps. They're 50 micrometers in diameter. So you're hundreds, thousands of amps per square millimeters every day in front of you. You don't even notice. Then those are examples of stuff we've done. Like here, it's 500 amps, and you can see the silicon as soon as we cut the heat, the current, poof, silicon absorbs the heat directly. 500 here. Here, 6,000 when your wire is aluminum of 3 microns only onto a big piece of silicon. Here, 30,000, but the pulses are short in time, and the wire is tiny. And here, 80,000 amps per square meter, the pulses are a bit longer. And if you go to 90, sometimes you have problems. And in Louis Néel, 20 years ago and still now, when they pulse 3,000 amps, not amps per square millimeter, amps, in a tiny wire that's here as narrow as 50 micrometers, you go to 2.5 million amps per square millimeter, but the pulses are 50 nanoseconds, okay? It's all a question of where does the heat go? Can I get rid of it? If I can, then I can have an awful loss of current, which means that in that tiny one wire loop, you can produce 50 Tesla during a very short time, but you can produce them. And here in the middle, you can put your little sample and you're in a lab and you can see what happens to your sample in a very strong field. What's in a magnet? In a magnetic microsystem? You've got coils, of course, you've got magnets, and then you have iron and magnetostrictive material. You can use demagnetization because of getting too near the Curie point, shape memory, magnetic shape memory, superconductors, diamagnetism. I will go very briefly on a few. Let's start with coils. You take a wire, you wind it, it's a coil. So some people do that with wires of 9, 10, 16 micrometers. And those, that's Benatav, but it's one of many. And they do that for medical sensors. Here we've got a 3-dimensional medical sensor that will tell you where your system and how it's oriented within a big external magnetic field. Say, oh, my thing is not lost in my patient. Maybe I'll find it. That looks impressive because it's it's an electron beam microscopy, but electron beam microscope. But it's the same dimension, except that it's wound on iron nickel parts made by microtechnology. So you get one step towards MEMS, MEMS. And then you can do your coils planar. So you do planar heads at the time where it was still used for writing with thermal laser assisted. You do printer heads for paper, ink paper, magnetic ink paper printers, industrial. You can do transformers if you have several layers and several coils together, videotape heads, magnetometers, and those are photos that are 20 years old. So if you go today, you'll find much better everywhere. And Nora will also talk to you about what coils could maybe do with biology and stuff like that. And you can make more complex microtechnological planar windings and all that. Now you have coils, but then you need magnets as well. So 4 main families of magnets. First one, you take a big good magnet and you just crop it down and grind it and machine it and polish it and you're happy. Except that when it gets a bit too small, then it's a bit difficult and the grains don't like that. Or you can take the powder, bond it with resin, and then you mold it into microtechnologically produced molds. So it's much cleaner, much nicer, but it's ferrites or rare earths, but it's bonded powder. So you lose in quality, but you gain in integrability. You can electroplate atom per atom, alloys most of the time, iron platinum, cobalt platinum, and a few others. And that's perfectly adapted to microtechnology, even though the materials themselves need to be annealed at high temperature if you want them to be of high remanence and coercivity. Or, and Nora will talk about it later on, the best you can get is to take a superb rare earth magnet and sputter it onto your microtechnological device, silicon or other, and then you have fantastic material, fully dense, oriented, but it also has its problems and its difficulties in making. So very briefly, that's to show you a few. I'll give, yeah. But you can make motors. You can. I'll show you a few examples. I'll go fast on that slide. That's a massive bulk magnet being machined and made smaller. You can bond powders, and Boris will talk about that later on. And that's great because you can take all the shapes you want, even though you lose in material quality. Those are electroplated. And here, those magnets, the middle one, the black one, goes up and down out of plane of the photography and is free moving. And here it's stuck to the ceiling, a glass ceiling of it's a glass substrate, this one. And 1, 2, 3, 4 magnets were embedded in the glass, and they retain him. They say, no, don't go away until you get an electromagnetic pulse to move away. And that's all electroplated, perfectly adapted to all those difficult shapes. And Nora will talk about that, like fully dense, sputtered neodymium marons and samarium cobalts. And once you have coils and magnets, you can also play with other stuff. And the funny one is diamagnetism. And you go online, you'll find hundreds of stuff, but here's florilege. So you go from flying froglets to magic. So that's the flying froglet. This one is 20 years old. It's probably dead by now, but it didn't die in the experiment. It's just dead because it's 20 years ago. And oh, the film is dead as well, apparently. What happened there? Can anyone see me?
Orphée, I think you need to share the screen again.
Yeah, I realized that. Yeah, it's it died on me. So okay, we are here. So where's the sharing? Sharing, écran partagé. Okay.
Yep.
Up to the beginning.
Yep. Yeah, we'll.
That's okay.
Yeah, there we are. So that's the flying frog, and after the flying frog, he's very happy. Justin was there at the time, and he tells me that the frog didn't die in that huge magnetic field. So diamagnetism, levitation for idiots, for dummies. So you take a magnetic material, you are diamagnetic, I am, but everything is diamagnetic except that a few things get so ferromagnetic that you don't see diamagnetism anymore. But we all are diamagnetic, except that the susceptibility of diamagnetism is between -1 to -400, 10 to the -6, instead of a few hundreds or thousands for ferro. So you don't see that. But okay, so if you magnetize anything, yourself, a frog, the moment will be blah, 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 and the force applied to it, if you have a gradient, will be blah, 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 multiplied by the gradient. And you remember what I was saying about micromagnets, they give big gradients. So if you are capable of making a big gradient, you're capable of putting a force on something that's stronger than gravity, hence the frog. So you can also do that on strawberries if you are a vegetarian, or on green chartreuse if you're an alcoholic. But you need a bitter electromagnet, and that sucks up 6 megawatts. Oh God, don't tell me the film has died again on me.
Yep.
It's died on me. Okay, so diamagnetism is not good for films. Where am I? That was 40 something, yeah, 35. So I'll go straight to 37 so I don't go through that bad slide. It said 6 megawatt of power for one frog. So it's not very good for ecologists who don't want to fly with airplanes. That's even more expensive. So you can do it without megawatts, because the force applied on a flying little object
Sorry,
is...
Orphée, we don't see the presentation.
It has lost that to God. Écran partagé. Okay. There. So you try and do that with 0 megawatts instead of 6 megawatts of magnetic coil, because the force applied on that frog or that oh, you hadn't seen the, well, anyway, it killed the film, so I won't. Is proportional to the chi, the susceptibility, but that's fixed. Water is -10, graphite is -500. Once you have your material, you cannot change its susceptibility. The volume, it's a volumic force, and therefore you don't care about that, apart from the fact that the machine would be too big. And the magnetic field, so you're at the maximum on, you're at 11 on susceptibility. You cannot go further than that. So you say, okay, what about the magnetic field? Well, once you go to 5, 10, 20 Tesla, then you cannot go further either. You're at 11 as well on the dial. So that's where you'll fight, is with the gradient. With the gradient, if you miniaturize everything, gradients go up, and there you start fighting against gravity. So those examples are very old as well. They're probably 20 years old. You put graphite, highly oriented pyrolytic graphite, onto a couple of magnets oriented north-south, north-south, so they give gradients at the edges, and it flies, and you can play with laser, and you can make them move. And that's forever, free levitation for infinite time. But that's limited. You cannot do anything bigger than that, because that's the best magnet and the best material with -450, 10 to the -6 in susceptibility. But if you want to get something else to fly, like something interesting for researchers, well, chi is smaller and mass per unit volume is bigger, so you have to make smaller things. If you want to make a magnet fly over graphite, magnets being density 9 instead of 2, you need to go smaller and smaller. And here we split a tiny magnet of less than a millimeter in 2 to create gradients all around it. And it flies here over graphite. And then at Nora's lab, it was the same, but with a single flake of neodymium iron boron of 10 microns thick. And it also flies for free over a piece of graphite as well. And you can start thinking of playing with micro robotics and floating things with that. Then you can start floating bubbles or droplets of water in air. So the diameter of those bubbles is about 30 microns droplets. And the gap in that permanent magnet is 1 millimeter in diameter, 1.5. And here you can start having fluidics without contamination, without gravity, so you can grow crystals of DNA or what you want, or proteins, to see what happens to them in space, without needing to pay for a satellite and go up there. You can also, if you go even smaller, you can also fly bismuth in air in between 2 bars of neodymium iron boron as well in Nora's lab. Those dust of bismuth can fly even though they're heavy, because it's even smaller, so the gradients are even higher, so you can fight against that mass density. You can also, in MEMS, as well as in massive systems, in small systems, you can use magnetostriction. And here it's another example of the triangle I showed you at the very beginning of my speak. And here we've got something that's about 1 millimeter long altogether, and the beam in the middle is about 200 microns long, and it has a layer of piezoelectric of 30 nanometers, on top of which 75 nanometers of iron cobalt boron magnetostrictive amorphous material. And when you give voltage to the piezoelectric here and here, it stresses the beam, so the magnetostrictive gets stressed. And you can see on the moons there, on the roundels, you can see that when from -1 megavolt per meter to +3 megavolt per meter, you align perpendicular or longitudinal because you stress by compression or you stress by pulling on the beam. And therefore, the magnetostrictive atoms, they say, ooh, I'm being pulled apart or I'm being compressed. And since my easy axis in my material is perpendicular or parallel to the stress, I will align perpendicular or parallel to the length of the beam. And you can see in blue and red, the easy and hard axis loops swapping directions. If you put 1 megavolt or plus +1 or -1 megavolt. You can make it hard or soft, so you can tune your radio frequency component if it was such a component in the system. You can play with the easy axis with voltage on the piezo, and the piezo talks to the magnetostrictive, and that's much easier in small things. If you make it bigger, that one, the film on the top left, it's two such things, but much bigger. They're a few centimeters each, and in sandwich between those two Kapton clad piezoelectrics, I am rotating that easy axis, and the magnet, the permanent magnet that has been put on top of it, sees the rotation and says, "Wow, I'm going to follow that," and you can make a motor. But reversely, on the second film here, if I rotate a big magnet in front of that, on that film here, you can see the roundel of magnetostrictive material glued in the middle, that black one. If I rotate the magnet, I can see that I have a voltage in the piezo because the magnet talks to the magnetostrictive stresses the piezo, and the piezo gives volts. And you can see that no matter what speed, quick or slow, the amplitude of the voltage is the same because it's not due to induction, it's due to stress. And so you can make a very slow either energy harvester, and we did a startup company called Energy, either sensors, etc. So it's multiferroics or composite multiferroics. And that's very also fun in microsystems. Now, microsystems, I have a few minutes left just to tell you about what you want to do with them. So I will probably cull because I have too many examples, but what
5
for?
minutes, Orphée.
5 minutes. Okay, so first thing, an example of what happens to a coil talking to a magnet. Big loudspeakers go to headphones, 10 times smaller go to earphones, 10 times smaller go to inside the head, an implant. They all work on the same principle with the same power ratio, power to mass of the actuator, except that when they go smaller, you have to go nearer the ear to hear them, but it's still the same system all the time. Now you can also go the other way around if my mouse accepts. From there, you can go bigger to another big loudspeaker, and you can go even bigger, but that's a different system. But it's always a coil and a magnet, and it still works. Now, that membrane, instead of moving air for sound, it can move photons. And if you deform a mirror in the reverse deformation that the atmosphere has deformed the image from the galaxies, you clean up that image and you can see that it's 2 stars instead of 1 here. For that, you need to move that little membrane, and one way of doing that is to put magnets on the membrane, coils opposite. And 20 years later, you have a company called Alpao in Grenoble, who is one of the leaders in the world to make deformable mirrors for adaptive optics, either ophthalmology, astronomy, etc. And funnily enough, we started with real coils with wires and real magnets glued instead of micro-technologically built coils and magnets. And 25 years later, it's still hand-wound coils and hand-ground magnets because you don't need to have silicon everywhere all the time. But that's a bad example. But it's an example that shows you that micro-technology doesn't mean the end of old-fashioned technology. What can you do with photons and magnets? Well, you can have a head-up display, so you need a scanner that scans with a laser on the screen of the fighter pilot, all the lives he has left. And so for that, one way of doing that is a mirror that can go left and right, X and Y, with a laser on top of it, and under it, hiding there, are a few mini magnets. And if you go smaller, and that's a patent we had with a company that was sold to the Japanese, and that goes into the next generation of mobile phone beamers. You can do motors. Those motors here at the bottom, they're the smallest commercial one. It's 1 millimeter diameter. It's a real magnet, a real coil, but you can start a bit bigger here, having integrated coils and powder magnets, and you can make them smaller. And so you can make generators or motors. I'll go quick on this one. I'll also go quick on this one. That's a turbo generator that gives you 3-phase. And that's also made with massive magnets, but integrated coils. you can hear under those wires is a flying magnet that we've seen at the beginning, and that's a switch that goes left and right. Here you can see it going, well, left and right on the film. And that can make integrated micro switches with flying magnets. I won't deal into this one. It's the same one, but out of plane instead of in plane. And I'll finish with where's the money? Well, in everything that has an actuator, but smaller. So micro pumps, micro switches, in the phones, in the fiber optic switches, in ophthalmology, in non-invasive surgery, in implantable devices, if you have a pump or a valve. Now, I'm talking about where's the money for MEMS in general, not all magnetic. Magnetic MEMS are a tiny part of MEMS in general. Electrostatic take a vast majority of actuators and sensors, but that's another class and it's not for today. It's another discussion, but you have them everywhere. And magnetics are slowly taking their share. And I haven't talked about sensors because A, I'm not an expert in sensors, and B, it's yet another fully huge class. So it was a mess, but you get the global idea. And I thank you for your attention.